Hi everyone! Today's video is my personal challenge. We will build an image recognition model with Python. And why is it my challenge? Because I've never built an image recognition model before. I usually work with retail companies and fintechs, so I work with customer data, I analyze text, but I never had an opportunity to do an image recognition project. If you're new to this channel, I'm Karina, I'm a finance person, turned data analyst, turned data scientist, and now I share my knowledge with other people online. Let's briefly talk about deep learning. Deep learning is a subset of machine learning that involves algorithms inspired by the instruction functions of a human brain, called artificial neural networks. It is a part of a broader field, artificial intelligence, and focuses on learning large amounts of data using multiple layers of neural networks. Image recognition is a task commonly performed using deep learning models. Why deep learning for image recognition? First of all, feature learning. Deep learning models, especially CNNs or convolutional neural networks, can automatically learn hierarchical features from images. Lower layers may learn edges and textures, while higher layers can learn more complex structures like shapes and objects. Another reason is high accuracy. Deep learning models, given sufficient data and computational resources, typically achieve higher accuracy in image recognition tasks compared to traditional machine learning methods. Common deep learning models for image recognitions are: the first one is CNN or convolutional neural nets. CNNs are the most commonly used deep learning models for image recognition. They consist of layers like convolutional layer, pooling layer, and fully connected layers that can effectively capture spatial hierarchies in images. Second one is pre-trained models, and this is what we will be using today. So models like ResNet, VGG, Inception, and others that have been pre-trained on large datasets. Third one is transfer learning. Using pre-trained models and fine-tuning them on specific datasets is common practice. This allows leveraging existing knowledge and achieving good performance even with limited data. Let's begin. This project will make your computer hot because once we start training the model, it takes so much computational power that everything just heats up. First of all, we need to install TensorFlow and Keras. This is the modules that work with neural nets. We will also do split folders and OpenCV Python. I found data at kaggle.com, link in the description, and for this specific case, I used agricultural data that has, I think, 30 folders, 30 types of different crops, for example, cotton and lemons. After we installed our libraries, in my case, all requirements are satisfied, we need to import libraries. The modules we will be using, we will import TensorFlow as TF. From TensorFlow Keras models, we import sequential. From TensorFlow Keras layers, we import convolutional or conv2D, max pooling 2D, flatten, dense, dropout, and input. Then from TensorFlow Keras preprocessing.image, we import image data generator. Then we import matplotlib, pyplot, splt, import numpy, snp, import split folders because all our data is located in folders. Import CV2 from TensorFlow Keras application ResNet 50, import preprocess input, and from TensorFlow Keras import layers and models. Let's briefly talk about all the modules that we will be using. So TensorFlow is a comprehensive open source platform for machine learning. It provides a flexible ecosystem of tools, libraries, community resources to build and deploy machine learning applications. TensorFlow and Keras modules, they use for building and training deep learning models. Image data generator we use for data augmentation and pre-processing. Matplotlib and numpy for data visualization and some numerical operations. Split folders and OpenCV for data organization and image processing. We needed to access our files. Preprocess underscore input for preprocessing input data to match the format expected by our model, and the model will be ResNet 50. Now we imported all our libraries. We need to read our files. So when you follow the link to the dataset, you will download big folder agricultural crops that has plenty of little subfolders. In all other projects, we read the file, then we analyze file, clean it, and create the model. In this one, once we read our files, we will split it in 3 sets. So we will split it into training dataset, testing dataset, and validation dataset. So 80% training, 10 validation, and 10 test. At first we say what input folder is. I'm saying input folder equals and the path to the folder I downloaded from kaggle.com. Then I'm indicating what will be my output folder. Now I need to say what will be the split ratio, because we want to split the data into 3 different folders. So I'm saying 80% will be our training, 10 validation, and 10 test. And I'm saying split folders dot ratio brackets. We use data from input folder. Our output equals output folder, because this is where we want to save our file. Seed 500, ratio equals split ratio. This is the ratio, and group prefix none. And a seed value, in my case it is 500, it is for the random number generator. Setting a seed ensures that this split is reproducible, meaning if you run the code again with the same seed, you can get the same split. In other machine learning models, we usually use random state to split our data, and again, random state is for this reason. So if you have the same data, use the same random state, you can replicate the results. Let's run it. It's saying that it copies all the files, and it's finished. Now we need to define the parameters. So image size equals 224 by 224 and batch size equals 32. In this case, each image will be resized to 224 by 224 pixels. This is a common size used for many deep learning models, including ResNet 50. A batch size of 32 means that the model will update its weights after processing 32 images. Now we will do also data augmentation for training data. So this is very useful for expanding the training dataset with transformed versions of existing images, which can help improve the model generalization. Pre-processing function equals pre-process input. This applies the pre-process input function from ResNet 50 model to each image. The function scales the pixel values to the format expected by our pre-trained ResNet 50 model. Rotation range 20 randomly rotates the image by up to 20 degrees. Width shift range 0.2 randomly shifts the image horizontally, left, right by up to 20% of the width. Height shift range 0.2 is randomly shifts the image vertically up and down, also by up to 20% of the height. Shear range applies random shearing transformations. Zoom range 0.2 randomly zooms into the image by up to 20%. Horizontal flip true randomly flips the images horizontally. Fill mode nearest, when the image is rotated or shifted, a new pixel need to be filled in. The nearest pixel values are used. Let's run it. No problems. And now we need to do data augmentation for test data, only rescaling, and for our validation data, also only rescaling. We say test underscore data gen equals image data generator brackets pre-processing function equals pre-process input. For our validation data, we say valid underscore data gen image data generator brackets pre-processing function equals pre-process input. For our test and validation data set, we applied this the image data generation function to rescale the pixel values without any additional augmentation. This ensures that the test data remains consistent and is not altered by random transformations. And we do exactly the same with validation data set. Let's run it. No problems. Now I will set paths to our training, validation, and testing data. So I say train underscore directory equals os.path.join brackets output folder comma train, and then I'm doing exactly the same for validation data sets and the same for test. Train underscore dategen.flow from directory. This method generates batches of tensor images data from the directory specified. Train data equals train underscore datagen.flow from directory. We say the path to our directory. Target size equals image size, which we specified before, batch size we specified, and a class mode equals categorical. Class mode, this type of label arrays to be returned. So categorical means that the labels will be one hot encoded, useful for multi-class classification. This process will create a generator that will read the images from the training directory, validation directory, and testing, apply the specified augmentations that we've done before, and prepare them in batches for training the model. Let's run it. Okay, it shows us that we split our data. If you want to print any random image from one of these folders, just to see how they look after being processed, augmented, we say images comma labels equals next brackets. I select validation data. IDX equals random dot rand integer brackets 0 image dot shape 0 minus 1. So we will print any random image from our validation dataset. PLT image show images IDX and PLT.show to display. And if we printed. This is how image look like. Augmented image looks like this. Now it's time to load our model. So from keras.application.resnet import resnet50. So I will be using pre-trained model called resnet50. And I'm saying base model equals resnet50, brackets weights ImageNet, include top false, input shape image size 0, image size 1, 3. So let's talk about the details. So resnet50, this is a specific architecture of CNN, so convolutional neural nets, that has been pre-trained on the ImageNet dataset. ImageNet is a large dataset containing millions of images across thousands of categories. Weights equals ImageNet specifies that we are loading the weights of the model that have been pre-trained on the ImageNet. Include top equals false. This means we are not including the fully connected layers at the top of the network. The top refers to the classification layer that are normally at the end of our network. By excluding this, we can add our own custom classification layer suitable for specific problem. And input a shape. This defines the shape of the input images. The images are expected to be size 224 by 224 pixels with 3 color channels, RGB or red, green, blue. And now we need to freeze the convolutional base. So we will say base model dot trainable equals false. This will freeze the convolutional base of the model, meaning the weights of these layers will not be updated during training. This is done to preserve the pre-trained weights and only train the newly added classification layers. Freezing the base model helps to leverage the features learned from the ImageNet dataset without altering them. Let's run it. Now it's time to build our neural network models using Keras sequential API, which allows us to stack layers one after another. Model equals models.sequential brackets square brackets, we say base model, that's what we refer to, layers.global average pooling 2D, layers dense 1 to 8 activation ReLU, layers dropout 0.5, layers dense 30 activation softmax. So our base model, as I said before, it's our pre-trained resnet50 model. Global average pooling 2D is often used to replace fully connected layers in CNNs to reduce overfitting and the number of parameters. Dense 1 to 8 and activation ReLU. This is fully connected dense layer with 128 neurons, and ReLU or rectified linear unit is activation function. This ReLU activation introduces nonlinearity, enabling the model to learn more complex representations. Dropout 0.5. This layer randomly sets 50% of its input units to 0 during each update during training time. It also helps to prevent overfitting. Dense 30 activation softmax. This is another fully connected layer with 30 neurons and a softmax activation function. So softmax activation function converts the output logits into probabilities, with each neuron representing the probability of a particular class. The sum of all these probabilities will be 1 or 100%. Let's run it. Now we need to compile our model. So we say model.compile optimizer Adam loss equals categorical cross entropy matrix accuracy. The optimizer is responsible for updating the model's weights during training to minimize the loss function. Adam stands for adaptive moment estimation. It's not a name. It is an advanced gradient descent algorithm that adjusts the learning rate for each parameter based on estimates for lower order moments. There are other optimizers, but looks like Adam is widely used because it's computationally efficient and requires little memory. So loss function in machine learning models measures how well the model's prediction match the true actual values. During our training, the optimizer tries to minimize the loss. So the less our loss, the better. So this is actual, this is our loss. The further it is, the further we are from actuals, and the closer we are, the closer our predictions are to the actual value. There are different types of loss functions, for example, mean square error, which is often used in regression tasks when we're predicting a number, and another version is this categorical cross entropy, which is often used in classification tasks when we're trying to predict a category. Metrics accuracy. Metrics are used to evaluate the performance of the model. They're not used by the optimizer, but provide additional information for you as a user. And accuracy, the metric calculates the ratio of correctly predicted instances to the total number of instances. And for classification problems, it is a metric that is commonly used to understand how your model performs. And now it's time to train our model. Model.fit bracket, we use our train data, comma, number of epochs, comma, validation data equal valid data. What I found, a lot of people use 100 epochs. I will use 25. Training the model takes very long time. So for example, that was our first epoch and it took 39 seconds. It shows this is our accuracy, this is our loss. So what we're trying to achieve, that with every new epoch, our accuracy improves, it increases, while our loss decreases. So when I was doing this project for the first time, when I was getting ready for this video, I'll show you. I used 100 epochs. It took me a very long time. It says 30 minutes, and you can see that my accuracy went from almost 5% and loss 3.8. It went down up to accuracy 95 and loss 0.17. Total accuracy was 85% and it worked very well. Let's see how it performs now when I chose just 25 epochs. So epoch is one complete pass through the entire training dataset. So when you say 100, the model will go through the whole training dataset 100 times. This number can be adjusted based on the specific needs on the training process. We train the model on the training data and then we validate in results against validation dataset. So this validation data is used to evaluate the model's performance at the end of each epoch. That's why usually we split our data into training and testing. So we use training to train the model and then we check the results on the testing dataset. With these more complicated models, you split the data into training, testing, and validating dataset. So you're training the model. At the end of each this run, the model checks how it performs against validation dataset. And then later we will use our testing dataset to check how well overall model performs. So if we talk about this training loop, our model initiates a loop that iterates over a specified number of epochs. In each epoch, the model processes all batches of the training data provided by train data, and then this optimizer updates the model's weights to minimize our loss function. Then we have this validation, and after each epoch, the model evaluates its performance on the validation data. The validation metrics like accuracy and loss, they're recorded, but they are not used to update the model weights. So it's just for you as an information. While the model's training progress is typically printed to the console, showing the training loss, training accuracy, validation loss, and validation accuracy for each of those epochs. And this information helps in diagnosing issues such as overfitting, where the training performance is good but validation performance is poor, or underfitting, where both training and validation performance are poor. Our training is finally finished, so we had 25 epochs compared to 100 epochs that I had done before. You can see that accuracy was going up and down, so maximum one we achieved is 84% and our loss was going down. Now let's evaluate our model on the test data. So we say test underscore loss comma test underscore accuracy equals model dot evaluate bracket in the bracket test data, and we will print the accuracy score because we want to know how accurate our model is. So let's run it, and the accuracy is almost 81%. When I was playing around and I had my 100 epochs, the accuracy was 86%, and in this case the accuracy is 81%, so not such a huge difference. So we have 30 classes in our dataset. Let's create the dictionary with our classes. It will be class names equals curly brackets, because dictionary is always surrounded by curly brackets, and then cherries, coffee plant, etc. When the model makes a prediction, it outputs probabilities for each class. The index of the highest probability corresponds to the predicted class. This dictionary that we've just created allows you to convert the index of the predicted class back to a human readable format. let's create a function that will help us to make predictions. So first of all, we will run this line of code. We creating a function called predict image. To create function in Python, we say def, then the name of the function will be predict_image, brackets image comma model, then colon, test image equals cv2 im read image. We will resize our image, expand dimensions, and then result equals model.predict test image. As a result of this function, we will print the class name. So we will print what this image represents. cv2.imRead brackets image. This function reads the image from the specified file path. The image is read into an NumPy array. cv2 resize. This function resizes the image to 224 pixels, which matches the input size expected by the model. NumPy.expand teams. The function adds an extra dimension to the image array. Model predict. This function uses the trained model to make predictions on the input image. NumPy.argMax result. This function returns the index of the maximum value in the result array, which corresponds to the class with the highest predicted probability. Class names square brackets r uses the class names dictionary to map the predicted class index r to the corresponding class name. Let's run it and let's use it to make some predictions. So we will say predict_image brackets, then we give a path to a file. I picked a random file, and then comma model. Since our file is located in this jovar folder, we expect that our model will return jovar. So let's see. It predicted correctly. Let's use another one. So this time I'm using an image of tomato, image 6. Again, predict image brackets, the path to our file, comma model. Let's print it and result tomato. To save your model, we say model.save brackets, then you indicate the name of the model. It's up to you, .keres. That helps us to save our model. So other things that can be done to the model, first of all, you can fine-tune the base model. Currently, we are freezing our convolutional base of ResNet 50 model. Fine-tuning of a few layers of the base model can help improve performance, especially if your data size is substantial. Another thing which we can do is use a linear rate scheduler. A linear rate scheduler can help in reducing the learning rate during training, which often helps in fine-tuning. Other thing is early stopping. Early stopping can prevent overfitting by stopping the training process when validation loss stops improving. The other thing we can do is to keep doing data augmentation. So we already use some parameters, but we can also adjust, for example, brightness, contrast to our images. If you're still unsatisfied with the results of your model, you can do batch normalization. So adding batch normalization can stabilize and improve the training process. If you noticed overfitting, you can add L2 regularization to reduce the overfitting. That was fun. That was my first image recognition project. I hope you learned something new with me today, and don't forget to like and subscribe if you enjoyed this video. I hope to see you next time.